This is a second part of our introduction to proof by contradiction. Now recall, in a previous video, we said our goal is to prove that a statement P is true. If P is true, then we know that its negation must be false. So what we do in proof by contradiction is you make the assumption that the negation of P is true. Now again, we know that can't be true. That leads to a logical contradiction, which says our assumption must be false. Our assumption cannot be true. That says that the negation of P must be false, because assuming it's true leads to a contradiction, which says that the original statement must be true. Now, many statements in mathematics, as you already know, are conditionals. P implies Q. If you're trying to prove a statement that P implies true P implies Q is true. So that's our goal. The statement we're trying to prove is we're trying to prove that the conditional P implies Q is true. For by contradiction, you assume that its negation is false. In other words, you assume the statement is false. Well, what's the only case where P implies Q is false? It's right here. If P implies Q is false, what we know is that P must be true and Q must be false. So in your assumption for proof by contradiction, what do you assume? You assume that P implies Q is false, which is basically what you're assuming that P is a true statement, the hypothesis, and Q is a false statement. Those are the only conditions where P implies Q is false. What we hope, if the original statement is actually true, this assumption will lead to a contradiction. That says that our assumption that P implies Q is false cannot be true, which says that P implies Q must be true. So let's look at this in a fairly simple example. We'll look at a few more complicated ones in a bit. But the statement is, it's a tough one. We've done this one by proof by, contrapositive, but we'll do this one by proof by contradiction. So we're going to do a proof by contradiction. The hypothesis, the P, is that n squared is an odd integer. The conclusion, our Q, is that n is an odd integer. Okay? So in proof by contradiction, we're going to assume that P is true and Q is false. So we're going to say our assumption, assume that n squared is odd and n is even. Okay. Now we know that can't be true, right? Because those we know that the original statement is true. We've already proven it in class. So this assumption has to lead to a contradiction. Our goal is just now to find it. I have this and statement. I'm assuming it's true, so I know both parts are true. What I'm going to do is I'm going to start with the n is even. You can start with either one, but I'm going to start with n is even. So if n is even, we know that n squared, or n rather, is equal to 2 times k, where k is some integer. That's the definition of an even number. Okay, so if n equals 2k, we know that n squared equals, do a little algebra, 2k squared. And let's work that out. That equals 2k times 2k, or 4k squared. Oh, but that equals 2 times 2k squared. And we know we've had this great closure property. We know that 2 is an integer and k is an integer and k is another integer because 2k squared is 2 times k times k. All of those are integers. So we're going to call that L. So that equals 2L. Where L equals 2k squared is an integer. And that's by closure of multiplication. Let's think about what we just said. We've got n squared equals 2 times some integer. Oh, so by definition, n squared is an even number, or is even. Oh, but what did we assume up here? We assumed that n squared must be odd. N squared cannot both be even and odd. An integer is either one or the other. So this is a contradiction. Always identify. Good to identify the contradiction. Okay, that n squared cannot, just identify it, cannot be both even and odd. That's a contradiction of a known fact. So our assumption here that our original statement is false, that P is true and Q is false, that leads to a contradiction. Because our assumptions lead to a contradiction, that says that the original statement cannot be false. The original statement is true. So if n squared is odd, n must be odd. And that is our proof.